doing all this, and our Lyapunov exponent is just the log of the total distance divided by whatever our initial separation was, times the number of steps times dt, right? So this is a relatively simple and hopefully intuitive way to calculate the largest Lyapunov exponent, right?
Still kind of more of a, so you just run it so you see if it's maybe at a later date or if it's anything as we expect.
Sorry?
Warm up loop, I'm not really quite understanding. So we're running it so we see it's maybe at a later time, or?
Well, so we're when we set up that initial difference, right, we take it back to this pendulum example. So the pendulum example, so here we are in phase space, right, this is 0, this is, this axis is theta, this one is theta dot, right? So we have the pendulum hanging down, and we're just giving it a shove, right? The way I've set it up here, the shove that so it's different than what I actually have up, the way I've written the code, right? But the shove that I'm giving here is in terms of the velocity, the small difference. There's a small difference in the initial velocities I'm giving, right? Up here, it's a small difference in the position. Right, so I could have had it instead a second point that started over here. The thing is that I don't know how the Lyapunov exponents are oriented in phase space at any point, right? We're trying to get just the largest. And that's really all we can hope to do with this, because only the largest one is going to come out, because that's the one where we're going to see the big difference, right? The system, as we evolve these two systems in parallel, they're going to stretch along the largest Lyapunov direction, okay? So we've set it up in such a way that they're not oriented, they're almost assuredly not oriented with the largest Lyapunov direction. And by warming it up, it's naturally going to evolve so that they are aligned with the largest Lyapunov direction.
I think so. In order to get the result of computation.
Yeah, so that when we measure the distance, we're actually going to be, when we get to this point and we start actually calculating the distance, we are calculating the distance that is going to be aligned with the largest Lyapunov exponent, right? Whereas if we just started from over here, that difference is not, right? Because it's not aligned with this. Okay.
Dr. Luchko,
Yeah.
could you use this?
Okay.
Sorry. Thank you.
Okay. Okay, so this is a fairly, for the most part, this is fairly straightforward, but like I said, it only gives us only one of these. The Wolf algorithm that we're going to look at next actually gives us all of them. It's a little trickier to implement. But it is more useful in that sense. So it uses the same basic idea here, that we're going to have a some sort of small displacement vector that we're going to track how it stretches over time. So we're going to evolve the system parallel. in parallel, or multiple systems in parallel. The difference is that instead of just having these two sets of conditions that we're tracking, we're going to set up a vector of conditions. Okay? So if we have, once again, our driven pendulum, we have our 3 Lyapunov exponents. So we're going to have 3 dimensions. So we're going to have 3 vectors, right? 3 orthogonal vectors that we're going to evolve through space-time, or through phase space. Now the trick to this is that we want to keep all 3 of those vectors actually aligned with the 3 Lyapunov or 3 Lyapunov exponents and their respective directions, right? So as we go through time, we're going to track this vector that we're going to be following with is going to track how the Lyapunov directions are also changing their orientation. Okay? So we're going to have these displacement vectors, and the displacement vectors are advanced by the Jacobian matrix at each point in the trajectory. So let's write it down. Oh, let's just so I'm writing it down. Okay. So here, so the Jacobian is giving the derivative of the velocity of each of our generalized coordinates with respect to each of the generalized coordinates. So we have the first generalized coordinate here, so our theta, its time derivative, so theta dot, with respect to theta, and then with respect to theta dot, and then omega t. So we're only going to have a 3 by 3 here, right? And then we're going to have the same thing for the time derivative of theta dot, and then for the time derivative of omega t. Now the time derivative of our system, or of our displacement vector here, so we're going to have our unit vector of displacement, is going to be the dot product with the Jacobian. Okay? So this now just gives us a first order ODE to solve. Right? And we know how to do that because we have our Mikata. We have our numerical method for numerically solving these ODEs. So we can time evolve our small displacement vector here. So this equation can be integrated in time to give the displacement at a later time. And then the orthonormal, the k orthonormal displacement vectors will naturally align with the lambda 1 direction. So my numbering here is backwards. Lambda 1 is typically our largest Lyapunov exponent. So we have the same situation as if we have just the 2 dots. They're going to naturally align with the largest Lyapunov exponent. So when we evolve these vectors through space, through phase space, through time, they're all going to want to align with our largest Lyapunov exponent. So we're going to have these, they're starting on these 3 dimensions, and they're all just going to sort of converge in one direction and spread out. So what we do to get around that is the Gram-Schmidt reorthonormalization procedure. Right? So this is something you probably saw in a linear algebra class at some point. Getting some blank looks. Some nods and some blank looks. Okay. So, the basic idea is that we're going to take our vectors that have deformed, we're going to use our first vector here as sort of our anchor, right? So we're going to normalize it here to get V1 primed. So V1 primed is now, so if we, let's think about it this way. We started out with, and I'm gonna, for sake of convenience, I'm gonna take this as the direction of our largest Lyapunov exponent. I'm gonna call this one V1, V2, and V3. These are all vectors. Right? As we evolve it over time, so time passes, V1, we were fortunate that it was already pointing in that direction. It's going to continue to point in that direction, and if anything, it's going to stretch. Right? So it's stretching in that direction that has the largest Lyapunov exponent. So that's V1. But V2 is going to shrink and grow in this direction. So it's going to go like this. That's going to be V2. And then V3 is also going to do the same thing. So they're all going to be trying to do that. Right? So what we're going to do is then we go over here. So we've picked V1 as our anchor, right? It's the one that we're saying this one is the one that's aligned. So we're going to treat it that way. We're going to normalize it back down. And then over here, we're going to use it. So this is an inner product or a dot product between the two. So we're going to take the dot product between V1 primed and V2, and then take that in the V1 prime direction. And we're going to subtract it off of V2, and then we're going to normalize it over here. So now we're taking V2, and we're subtracting off this component that belongs to V1. And we're renormalizing it, and so we get a V2. Then we've really just removed that V1 component of it, right? So now they're going to be orthogonal to each other. And they're normal vectors, so they'll be orthonormal to each other. And then V3, we're basically going to subtract the components of both V1 and V2, and what's left over, we normalize that. So we end up back, so we're going to evolve the system, and instead of this time in the previous algorithm, right, we rescaled V1 so that we had that small distance again. What we're doing in this case is we're taking our stretched vectors here and we're resetting them back to the same basic condition that they were. Now, how this helps us is V1 is the one that's aligned, it's aligned with the largest Lyapunov exponent. The second largest Lyapunov exponent, once you take that out, once you remove that component due to that largest Lyapunov exponent from V2, what you're left with is the second Lyapunov exponent because it's the second biggest one, right? So the second biggest change in this vector length is going to be due to the second Lyapunov exponent. So it's naturally now going to be aligned with the second Lyapunov direction. And in this case here, because we only have 3, once we get rid of the components from those two, from V3, what we're left with there, it's got nothing else. It has to be aligned with the smallest Lyapunov exponent. Okay, so the idea here is now that we're going to evolve the system for a certain number of orbits. Anybody remember what an orbit is? No? Okay, remember our damped driven pendulum, right? So who remembers what a surface of section is? I heard something.
Where the motion is happening?
Sorry?
Where the motion is happening?
Not quite, no.
What was the cross section of the phase space that we were looking at?
Yeah, it was a cross section of the phase space. So remember we had, for our damped driven pendulum, we would have theta, theta dot, but then because we had that periodic force applied to it, there was this omega t that was a third dimension, right? It was periodic, so it was cosine omega t. So when we took that slice, we were taking it at, so this was periodic here, so we were taking it at a particular slice in time, right? So for example, we could have said, well, whenever, whenever this cosine evaluates to 0, or something like that, right? So our so because our system has this natural periodicity to it, we can call that an orbit, right? So our surface of section was coming through here, and so what we were doing is we were collecting, the way we can construct that is to collect a data point once per orbit and plot it in the theta dot and theta plane. Okay? So what we're doing here is we're actually doing this. N orbit is the number of orbits that we're going to evolve the system for, right? So the number of times we go through this periodic driving force, and tau is going to be the period of that orbit. So how long in time does it take? And then we're going to average over the number of orbits, and then we're taking the natural log of the norm of our vector, right? And so we're doing the vector, notice here now we actually have a subscript j, so we're doing this for each one of the Lyapunov exponents. So for each vector component, we're going to take its natural log. Okay, so let's back one more. Nope, not. Oh, I wrote it. Sorry. So sorry. Yeah, you can see the equivalent for our other algorithm is written up here. So it has very much the same form, right? Except we're not. This one involves the orbits. This one doesn't. This one is has multiple Lyapunov exponents, and this just has the one. So here, how does this look? So we're going to create our initial coordinate vector, V0 here, and then we're going to create K displacement vectors. So K is our number of dimensions. And we're going to initialize it to the identity matrix. So we're basically, we just need to identify initialize this to the identity matrix, right? So our identity matrix is 1 0 0 0 1 0 0 0 1. It's naturally composed of 3 orthonormal vectors. We're going to do our warm-up loop again. And now we're going to iterate and collect data. Here we're doing it over a number of orbits. And so then for J being the number of steps that we're going to evolve the system, or the number of steps we are using per orbit. We're going to integrate V0, our initial conditions, one time step. And then we're going to integrate one time step our displacement vectors. Okay? So our displacement vector is going to use V0 here as part of its input parameters, right? So that's going to be its star args there. So we're going to take then the total distance for each displacement vector, and then we're going to scale V1, the distance between V1 and V0 back to D0. So we're going to do our Gram-Schmidt reorthonormalization of our displacement vector here, and then repeat. And then we get over the outcome exponent at the end. Okay, so let's take a break here. When we come back, we'll do a little bit more about the, we'll take a look at this in the context of the damped driven pendulum. And then we'll hopefully then finish up the chapter. Okay?